I want to introduce to you the D-Wave 2000Q, how it's going to affect machine learning and optimization, and a little bit of the business strategy D-Wave had when creating and releasing this product. I'm going to go over a little basic introduction of optimization techniques and quantum qubits and things you need to know about quantum annealing. I'll go over a product summary of the actual D-Wave 2000Q, do a little timeline of the technology readiness level, go over some of the societal effects and impacts, and I will go over a brief amount of the intellectual property that D-Wave holds of value. I will try to do an opportunity analysis on how they think they're going to actually get profit from this product, and go over a little value chain analysis business model that D-Wave has, and of course end with some conclusions. All right, so complex problems and algorithms. Algorithm that can run in polynomial time is an algorithm. If you have n inputs, it will run n to the x, where x is greater than 1 with that many steps. This is okay. It's a reasonable amount of time, but once you start going into the realm of non-deterministic polynomial time algorithms, the number of inputs n that you have actually exponentially increase the amount of time your algorithm is required to run. NP problems actually have a polynomial time solution though, so you can actually verify the solution of your x to the n within n to the x steps. NP complete problems involve NP problem which may not right away have a way of verifying it. You can transform that algorithm into NP algorithm, another NP algorithm with polynomial time steps to verify that solution. An NP hard problem, however, you cannot verify its solution without actually going through all x to the n steps another time to verify the solution. So NP hard problems are very contentious and important to solve nowadays. So quadratic unconstrained binary optimization, or QUBO, is an NP hard problem. It's very important in machine learning, and it involves minimization of this argument where this x is a vector and it's full of zeros and ones, and that is what you're trying to optimize, or you're trying to find the best x, that a combination of zeros and ones to optimize the problem definition Q. Q really holds the meat of what you're trying to solve for a particular problem, be it max cut, graph coloring, or partitioning. And I'll go over what those mean soon. Qubits they have the special property of being held in a state of superposition, where they can either be 0, 1, or they can be both at the same time. If you look at this diagram down here, you kind of see it's more of like a phase, like you can imagine this as a magnetic field and a direction pointing vector. If the magnetic field is pointing in the up direction a little bit, you can consider that qubit when read to be a 0. And if it's pointing down, you can consider it to be a 1 after being read. But you can put them in a state of superposition on this circle in the middle to be 50% of the time read 0 or 50% of the time read 1. So the D-Wave 2000Q quantum annealer itself, this is a picture of the 2000Q IC quantum processing unit, and this is hanging in a sub 100 millikelvin refrigeration tank with all this electromagnetic and thermal shielding, and all these are input and output pipes to that in which that magnetic information is converted into digital information going up into the outside world. It in particular is good at solving QUBO problems. A true universal quantum computer, as opposed to a quantum annealer, can actually solve two extra problems known as the Shor's algorithm and Grover's algorithm, as well as some other interesting properties, such as quantum teleportation and other things you can't really do on a quantum annealer. These problems are very important to solve, but solution to QUBO problems is very good to have, at least having that. The reason the D-Wave 2000Q only solves QUBO problems is that they're able to scale these annealing qubits way up. There's only about 50 qubits available in some of the largest quantum computers right now that are universal, but coming out later this year, D-Wave's got the Advantage coming out. That has 2,000 quantum annealing bits. So you can actually apply these bits to real world problems, whereas universal quantum computers still have a ways to go yet. A couple of people have bought this, Temporal Defense Systems, which is a cybersecurity firm, and the joint AIMS site between Google, NASA, and the USRA to further machine learning. The LEAP API is a product they kind of have come out with recently to allow people that don't have $15 million to have access to a quantum computer, or a quantum annealer at least. That costs about $350 per person for a monthly subscription. So the TRL timeline. In 1999, D-Wave was founded by Haig Ferris and Gordy Rose. They really had kind of an idea of what the technology they had going forward, as they're both academics and related. Haig Ferris was kind of a business guy, and Gordy Rose was really interested in physics and quantum computing and superconductors. After they kind of put things together, Gordy came out with the Orion prototype, which was 16 qubits and could instantaneously solve Sudoku problems. It really showed that a product could be made, and they had found people they could work with, such as NASA and their Micro Devices Systems Lab, to create the actual superconducting IC. 4 years later, the D-Wave 1, the first actual available quantum computer for sale, the minimum viable product, we'll call it, was released. And the technology had gotten a little bit better, but more so, the actual go-to market, since you're able to buy a quantum computer now, got better. And, well, they weren't fully prepared with what the customer wanted and what they knew the customer wanted, but they actually had a product at least. More recently, 5 years ago in 2015, they came out with this IC for the D-Wave 2X, which is the same IC as the 2000Q. And I think they did this to buy some time. The 2X had actually about half the qubits turned off. And that was kind of a smart idea from a business perspective, as they could gradually grow up a product and get customers acquainted with the same IC. Really, it was 18 years since 1999 to 2017. However, between the minimum viable product and now, well, 2017 or 2015, it was 48 months. We see a humongous, like greater than Moore's law, 10-fold increase from this 128 qubits to this processor that still had 2048 qubits in it. So the understanding of how to make this technology or the ability of it to actually function greatly increased. So a little bit of the societal impact of how this is going to affect us, and it really follows the common theme of what machine learning has already affected so far. The maximum cut problem actually affects a bunch of traffic flow and scheduling problems, as well as it can be applied to economics for portfolio optimization, communications for compression and beamforming for radar even, and it can actually be applied to IC design and physics itself for experimental solutions. And you can kind of see these two together will lead to better quantum computer designs just being run on their own quantum computers. But we will see that some of the computer science effects are not that good, such as, well, at least for us as a consumer. Targeted advertising will become better due to better pattern matching, and some crime analytics with facial recognition will become better. It's good and bad, but it's going to require a revamp of our privacy laws. It will also allow for easier hacking. The RSA encryption algorithm is based off of prime number factorization, and the 2000Q actually has a patent involved with it that it has patented a version of using only the annealing qubits to factor prime numbers. So if you can do that faster, you can decrypt all this saved encrypted information that corporations have been collecting on us. So the maximum cut problem itself, it tries to attempt to, if red is one set of vertices and green is another set, you try to find the cut or little circle here that maximizes the most amount of vertices between the two sets. And that has, as I said before, potential to lead to greater quantum computers, direct implications on traffic flow and congestion. They actually use the 2000Q at a conference with Volkswagen to automate bus schedules. It also affects communications and beamforming. The graph coloring and partitioning problems. Graph coloring is, you want vertices, if they're in different sets, you want them only to be connected by edges if they are of different colors. And you really want to minimize the total amount of colors available. This has direct effect on image recognition software, and it can be used for traffic scheduling and automation. The partition problem actually has a solution already in polynomial time, but it's only an approximation. Using hybrid digital and quantum computers, we can actually improve upon any partitioning of memory that computers are currently doing. So the societal impact, some of the other stuff, as I was saying before, better facial recognition and targeted advertising might require some external force or our own governmental federal laws to protect us. That can be modeled on the California Consumer Privacy Act that was recently released. That just basically says any website that's collecting information on you, you have, if you're a resident of California anyways, you have the ability to go in and see what information they have on you and choose to delete that. Quantum annealing, actually, for prime number factorization, if people can easily see all your banking records and passwords and stuff just through basic internet traffic, it will be really bad if someone uses a quantum computer for such an attack. It will be more of a concern when these universal quantum computers come up. The annealing method takes a little bit longer to crack the RSA algorithm, but we can take steps now to prevent this in the future by moving to standards that are quantum resistant encryption methods. Some of the intellectual property that D-Wave has associated with the 2000Q system itself, they have 70 different patents, and it really boils down to 5 main areas of interest. The quantum annealing principle itself, many software patents that are valuable if they can be defended, they really just describe using methods of using quantum computers, such as solutions to QUBO problems or using it for facial recognition, basically just applications. Patents dealing with quantum circuitry, and they have the other valuable area they have is more recently, meaning they have more to do with the 2000Q and 2X system itself, error correction patents. That allows for greater interconnectivity between qubits, and I'll show you what that means soon. Peripheral hardware patents such as refrigeration and thermal and electromagnetic shielding, they've patented some of that as well. So, quantum annealing itself involves preparing the qubits into a state of superposition. So they got 50% chance of being 1 or 0. Then you load that Q matrix into the system by impinging coupling effects between those qubits. And then you just wait between 1 nanosecond and 100 microseconds for the system to reach a steady state. You then read the magnetic fields of each qubit and convert that into digital information. So they've patented this many times, just trying to get quantum annealing. Quantum annealing will work on normal universal quantum computers too. So if they can defend this patent, then it's really valuable for them. Error correction. So I want to start by saying this is 1 qubit. It's basically just a wire. It's a big loop just tied at one end of superconducting material. So superconductors, you can impinge a magnetic field upon it and it will retain that magnetic field. So all you really need is just one unbroken loop. These two are just qubits. Here is where you load that qubit or prepare it into being in a superposition state. Up here is where you would read off a qubit junction. You read the magnetic field of the qubit. This is the important part. This determines the coupling strength between these 2 qubits or more qubits. If you have coupling strength of 0, these are 2 independent entities. If you have full coupling strength, this actually becomes 1 full qubit. So it's like a 1 long chain. If you do this though, it kind of introduces some interference into the system, and that's where this error correction ability comes into effect. This can correct for errors in ambient magnetic fields as well as interference created from coupling qubits together. So why this is important is you take 1 qubit, making a chain of qubits, and then you keep chaining them together. You can actually have greater interconnectivity because you can take this qubit, say on the furthest left side of the processor, and have it affecting through a really long qubit chain, a qubit on the opposite side of the processor. That's why interconnectivity and these coupling circuits are important. So some of the opportunity that D-Wave has in this is increasing the amount of parallelized computation without increasing system size or power. All possible answers are evaluated at once. So you could make the argument that if you have a supercomputer working on the same problem, the amount of power that it takes to run all those inputs at the same time, it really only takes one of these quantum processing units to do the same thing. Some of the competition that D-Wave has is in Google and IBM. They're making superconducting quantum computers, but of the universal nature. They only really got up to 50 qubits, and they're not selling these. The 2000Q system is offering the ability for anyone to access this for $350. So, although IBM does offer a free access to its 50 qubits, you can get 2,000 qubits and soon 5,000 by using the LEAP software. Rigetti Computing is a smaller outfit that is actually doing the same thing. They have patents on error correction, quantum logic gates, and I/O methods, and they are also selling online online time. There are other competitors as well that are not superconducting, but they have not made it as far as these three companies. Value chain analysis, we can see the most of what D-Wave does is R&D. They have to actually work with Cypress Semiconductor to create these neodymium superconducting qubit structures. And the most important thing, I'd say, they don't have many outfits, but the most important support activities I'd say they have to do with defending and creating these patents for this R&D and quantum processing unit creation. A lot of the people on the board of directors are mostly concerned with profit. They're all pretty much venture capitalists. So the question is, since they're breaking about even in selling these $15 million quantum computers and the LEAP software and paying all these engineers, where's the profit? Well, more people keep coming in. As they've been coming in, they've been kind of loaning money to this system, and they've been clearing about $30 million a year just from other venture capitalists. So the value that is there is that the 2000Q is the only sellable computer at this point, and it has the most amount of interconnectivity, and there's the LEAP API for anyone to kind of join in for $350 to $3,000 a month if you're a business. Kind of what D-Wave really does is sell, design, and maintain quantum computers. The value extraction of the 2000Q is they get about $15 million for one sale, but over 3 years, the maintenance costs about $9 million. So in conclusion, the 2000Q has great potential to affect many areas of anything that AI really touches in machine learning, traffic flow and computer science. The prime number factorization and facial recognition really is going to require new laws by our government to kind of go over and maintain. The patents D-Wave actually controls on quantum computing software are very broad, and they can stifle future innovation they should really just be copyrighted. The patents pertaining to error correction are very valuable. The more interconnectivity you can have, the greater and more stable the entire system is. And if those can be successfully defended, then they really they can go into the future with less fears. At this time, though, since D-Wave has transitioned to more of a LEAP model, like most of the customers are people that are just subscribing to the software. As soon as IBM and Google start scaling up their normal quantum computers, they're going to be in trouble. So the best thing that D-Wave can really do to protect itself going into the future is to either acquire another company or merge with, probably Rigetti Computing would be the best in order to survive. So they have a full quantum computer going into the future, and more of a diverse patent portfolio that is easier to protect. And so these are my
Sure said
references.
pool party.
Are there any questions?